All right, sorry for the interruption. Let's keep moving on. So delta x is 2 minus 1 meters, which is 1 meter. Delta v is equal to minus e sub x. Delta x is equal to minus 400 times 1 meter, which is minus 400 volts. So delta v is negative, which makes sense in terms of the energy principle. So you would expect it would be going faster, so you would expect a potential drop, not a potential gain, as it's going the same direction as the electric field. Now let's look at path opposite of the electric field. So in this case, we'll still have A at 1, 0, 0, and B over here. Now we're going B to A, same field. So delta V is equal to minus E sub x, delta x, which is equal to minus 400 times minus 1, which is plus 400 volts. And so delta U increases, which again is unsurprising. So pretty easy so far. Now let's look at path perpendicular to the electric field. So once again, we can go from B to A. But this time, our electric field is going to be going up in Y. And so here what we would see is delta V is equal to minus E sub x, delta x, plus E sub y, delta y, plus, well, 0 for the Z components. And this is equal to 0 volts per meter times minus 1 meter plus 400 volts per meter times 0 plus 0 is equal to 0 volts. So delta V is 0, but this is consistent with what we learned when we talked about work. You can't do work perpendicular. No work is done, so 0. So in summation, and this, by the way, when in doubt, double check yourself like this. The sign of delta V and direction of path relative to the electric field. So if the path is in the same direction, then delta V is going to be less than 0. It's going to be negative. Path is opposite of the electric field, then delta V is greater than 0. It's going to be positive. Then if the path is perpendicular, then delta V is equal to 0. And other conventions, just so that you're used to them. So delta V is equal to VB minus VA. Path starts at A and ends at B. And then delta V is equal to VA minus VB. Path starts at B and ends at A. And VA, V sub A means potential at location